So the way I want to wrap up this section on adiabatic changes is going to be deriving the molar heat capacity ratio for a perfect gas. So that's going to be ultimately getting to gamma. So we've already done this in lab, and like I mentioned in the last video, I feel like most people are pretty solid with at least being able to do the math to derive this. What I saw in the exam was really big assumptions and not building up from the equipartition theorem. So that's what I want to do here is just clarify how we're going to go from basic observations of the universe and build it all the way up to gamma, right? So it doesn't matter whatever, you can write math for anything you want, but it still needs to describe a physical process, right? So we need to start with actual observations based on reality. So first things to make our lives easy, we're just going to assume we have a perfect monoatomic gas, right? And so we've discussed this before. This particle is only going to have 3 degrees of freedom, so it can only translate, and that's going to be in the x, y, and z direction. Obviously, it becomes more complicated if you have a linear molecule, then you can rotate around its center of mass in 2 directions, and then at higher enough temperatures, which really aren't that high, you'll start to have access to vibrational modes, but that's a pretty big jump beyond classical mechanics. For us, we're pretty much focused just on translation and rotational. Even though classical mechanics can approximate the vibration of the bonds of a molecule based on Hooke's law, like it's actually like a spring, but we find out it's a little bit more complicated in real life, so we're going to keep it as a simple example here. So if we start with the equipartition theorem, basically what that's saying is that kinetic energy is going to be equally distributed through all degrees of freedom of motion. So in our case, that means the kinetic energy, the system is going to be, or a particle, is going to be equally distributed between the x, motion in the x direction, motion in the y direction, and motion in the z direction, right? So this is going to be based on classical mechanics. The reason why I'm going to bring in quantum is because that is the whole next semester of PChem for us. So we're going to keep it to as classical mechanics. And so we know our definition of internal energy, right, is the total sum of all the kinetic energy and all the potential energy in the system, right? That is the definition of what internal energy is. So we're saying, since this is a perfect gas, we already know that there are going to be no intermolecular forces. So that means no London dispersion forces, no dipole-dipole interactions, no hydrogen bonding, and no other types of intermolecular forces, right? So therefore, the potential energy is not going to change, right? We could even go to the extreme, because some of the potential energy is actually of the system is bound up in literally the particle itself, which can be calculated from E equals mc squared for its standing mass. And then beyond that, the amount of energy to just build up the molecule itself by actually putting electrons into each of the orbitals. It can get pretty complicated. The nice thing for us, though, is that we're going to assume that none of that changes, so potential energy actually just drops out of the equation entirely, because it's not going to change, right? So we're going to make the reasonable assumption that all the changes in internal energy can only come from changes in kinetic energy. So what I actually should do here to make this more correct is to put our infinitesimals in to indicate there's been a change in internal energy and a change in kinetic energy. So if we reach back further into focus, I believe that was the second section of focus 1, where we derived the root mean squared velocity of a perfect gas, of a single molecule in 3 dimensions, right? So we're dealing with a single molecule. So what we see here, we have the Boltzmann constant. There's 3 directions. If you go back through the derivation, you find out that's where that number 3 is coming from. And we know there's going to be a relationship between temperature and the mass of the particle. So if we simplify our math, instead of dealing with 3 dimensions right now, let's focus our attention on a single direction. We'll just pick the x direction. What we can do is cancel out that 3, and so the root mean squared velocity of a particle in the x direction is just the square root of the Boltzmann constant times the temperature at which the system is at, divided by the mass of the particle itself. We also have our definition of kinetic energy from physics, where we know it's 1/2 mv squared. This holds true over any mass with any velocity. So macroscopic, you can throw a baseball and figure out its kinetic energy. You can also find the kinetic energy of a subatomic particle based on this. The only thing is when you do get to the quantum level, mass is actually usually referred to as energy itself. But that's beyond this course, so we're just going to treat it as the mass of the particle, because it's large enough that we don't need to worry about those effects. So what we can do then is we can substitute in for velocity, if we're assuming the root mean squared velocity in the x direction, we can substitute this expression here in for this velocity variable here in kinetic energy, and this is our resulting equation. So the square cancels out the square root, and the masses cancel, so we're left with 1/2 the Boltzmann constant times temperature will be the kinetic energy of a single particle moving in a single direction, just the x direction. Now, if we look back up here, we know kinetic energy, any change in kinetic energy will be equal to the change in internal energy based on our assumptions. So what we can do then is we know U equals kinetic energy for all 3 degrees of freedom. And so if this referred to the x direction, if the equipartition theory holds, these variables here, this quantity, should then be equally distributed between the x, the y, and the z direction. So for us, though, we're dealing with single molecules, at least in our derivation right here. So that's why we're dealing with the Boltzmann constant. So if we want to convert to say, dealing with a mole of gas, so we're dealing with an actual quantity that is much more easy to deal with, much more easy to measure in a lab, the relationship between the Boltzmann constant and R is literally the Boltzmann constant times Avogadro's number, so for 1 mole of gas. Right? So we can rearrange so the Boltzmann constant is just the ideal gas constant divided by Avogadro's number. We can substitute that back in for our Kb. And so that's what we've done here. If we multiply both sides of the equation by Avogadro's number, it's going to cancel it out in each of the 3 terms on the right-hand side of the equation. This will leave us a U times Avogadro's number, which basically is the amount of U for 1 mole of gas, which can be written as U sub m, which is the molar internal energy. Right? So now that we're dealing with 1 mole of gas, and those moles of gas can either move in the x, y, and z direction, or any combination of both. So if we clean up this equation here, so this term plus this term plus this term cleans up to just the molar internal energy is 3/2 RT. We know by definition that the molar heat capacity at constant volume, so we're going to now impose the conditions of constant volume just for this equation. We're going to see we can actually now go and change the conditions afterwards, but to look at one specific example under constant volume conditions, we know that the molar heat capacity at constant volume is going to be the molar internal energy with its change with respect to changes in temperature while keeping the volume constant. We can substitute in our equals 3/2 RT into our derivative. Now we have the change in 3/2 RT per change in temperature at constant volume. If we take the derivative here with respect to T, right, it simplifies down to 3/2 R. And this is what we've seen before several times, that the molar heat capacity of a constant volume of a perfect gas is 3/2 R. If you were doing this for a single molecule, it would be CV equals 3/2 Kb, right? So we've already established a relationship between the molar heat capacity at constant volume and the molar heat capacity at constant pressure, right? So this was our original expression. So this is the heat capacity of a single molecule, Cp minus Cv equals nR. If we divide both sides by R, we now have the molar heat capacities, and their difference is going to be equal to R. If we substitute that in, we know Cp, all I did was flip over the Cv over to here, because I already know that number. I have this equation here. It's easier to do the math to find a common denominator. I'm just going to have R, because technically it's 1R. It's the same thing as saying 2 over 2. So now I have 2 over 2R plus 3 over 2R. My common denominator of 2, 3 plus 2 is 5. The molar heat capacity of a perfect gas is going to be 5/2 R. So to finally finish this off, to bring everything full circle, to deal with what we calculated in that second video that was posted, when we're dealing with the heat capacity ratio of a perfect gas, or any gas, but now we're dealing with a perfect gas, we just found out that CPM is 5/2 R, CVM is 3/2 R. We do some rearrangement, so instead of dealing with fractions over fractions, which are confusing, I'm just going to take the denominator and write it as a reciprocal. So there we go here. We see the 2's cancel, the r's cancel. We're left with, sorry, that should be 3/2. Oh, sorry, 5/3. My bad. 5/3 r is going to be your molar heat capacity of a perfect gas. That is my mistake. So I will change the document that has been uploaded to EC-Learn to reflect that. That was my mistake. So one last comment on adiabats, and so this is going to come up when we deal with the Carnot cycle. That we're going to be in focus 3 when we are proving that entropy of the system is a state function. So we've looked at, in focus 1, isotherms, isobars, and isocores, so constant temperature, constant pressure, constant volume. Adiabats are going to be a way we refer to the actual curve that you're seeing on a graph, right? So it's actually referring to the shape of the graph of a curve, but under specific adiabatic conditions. So what we can see here is a 3D surface, and this is projected on the 2D surface down here. So what we can immediately see is that in the red, the isotherm actually has a more gradual change in pressure as that volume is increased at constant temperature. But if no heat's being allowed to be exchanged with the surroundings, we actually see there's a steeper decrease in pressure as the volume changes for an adiabatic process. Mathematically, we can see because P is inversely proportional to 1/V for an isotherm. For adiabats, P is inversely proportional to 1/V raised to the gamma, so the heat capacity ratio, right? So if we read through my little summary here, right? So both isotherms and adiabats can be plotted on the axes of pressure and volume, and that's what we see there. Temperature is that third axis that's giving us our surface that we see in green. However, you can see that the adiabats fall more sharply than the isotherms. So under isothermal conditions, right, the pressure of the gas is going to fall more gradually as the volume expands, and the reason for that is because heat can be exchanged with the surroundings. So as that volume expands, right, a real gas is going to have to fight against those attractive forces being broken. So what's going to end up happening is the heat will be pumped in from the surroundings into the system to compensate for that. What that's going to do is actually increase the kinetic energy of the molecules. So technically the pressure is going to change more slowly because basically it's buffering that effect of changing the volume by dumping more heat into the system. And so the pressure is going to fall more gradually. In terms of an adiabatic expansion, there is no exchange of heat with the surroundings. So those molecules, as you're pulling them away from each other and breaking those attractive forces, there's nothing to compensate for that loss of the basic conversion of potential energy into kinetic energy. So that pressure is going to fall more rapidly because there's no offset of a flow of heat into the system. And so that's my last comment that I wanted to make on this section. I believe that is it.